Answering exercise 17.7 requires for you to have mastered a few things from Organic Chemistry 1, which we reviewed in a separate video. So for this video, I'm going to assume that you have mastered the material that we reviewed in that previous video. So here, they're giving us a conjugated pi system, so two conjugated pi bonds, and we're going to be adding a hydrohalogen, so a hydrogen bonded to one of the halogens. It's either going to be chlorine, bromine, or iodine. Fluorine is too unstable by itself because it's so small that it oftentimes, it's a very bad leaving group because of how small it is. It's not able to handle having a full negative charge in such a small space. So here they say predict the products for each of the reactions and crucially propose a mechanism for how it's formed. So first we're going to have our diene, and then we have our hydrohalogen. So here, hydrogen chloride. Now, as we saw, these pi bonds are nucleophiles, as we saw in the review video, and also this chlorine is slightly negative and the hydrogen is slightly positive. So what ends up happening is the pi bonds attack the hydrogen. And there are two ways that that can happen. Either and here let me just do this so we have more room. Either the first pi bond can attack the hydrogen, or the second one can attack the hydrogen. So let's duplicate this whole thing, and we'll consider each of those cases one at a time. Let's start with the first pi bond, the one on the far left. So if those electrons attack this hydrogen, the electrons in that bond go to the most electronegative place nearby, which is the chlorine. And so after that first step, and note that chlorine already has 3 lone pairs, when the electrons in that bond go onto it, it'll have a 4th. So here, we leave our second pi bond there. That didn't participate in this first step in this example. And the hydrogen would add to the carbon on the end because that gives us the more stable carbocation, as we discussed in that review video. Now that carbocation is allylic to the pi bond, and so it's going to have a resonance form. So whenever you draw those resonance structures, you draw brackets that warn people that neither of those structures is true. The true structure is the average of the two, so you draw that special resonance arrow with one line and 2 heads that tells you, take the average, neither of the structures drawn ever exists, only the average ever exists. And to draw the resonance structure, you would draw the structure you have, but the pi electrons go toward the positive charge, as we discussed in that review video. So we've got these like this. And so this pi bond will be here now, and we will have the positive charge on the carbon that those pi electrons left. So that carbon had those pi electrons, the pi electrons just left, and so it is left with a positive charge. So we have these two possible products for the carbon chain. The chlorine, meanwhile, has 4 lone pairs and a full negative charge. So it has 2 electrophilic places where it could attack. This is clearly our nucleophile with a full negative charge, and it can attack either one of these electrophilic positions. If it attacks the electrophilic position on the left, then you would end up getting one product. Oops. So the chlorine would attach here. If it attacks the electrophilic position in the other resonance structure, then the molecule you'd get would, and here we'd still have our pi bond here, the molecule you'd get would have its chlorine here. Now you'll notice 2 things about this. both of these molecules are actually the same. So if you take this molecule and you flip it over, so the chlorine starts to come out at you and then it flips over, it looks exactly like this. So they're actually the same, but the second thing that you'd want to notice is that the carbon that has the chlorine on it is a chiral center. So it has a chlorine, the weird carbon chain, a methyl group, and a hydrogen. That's 4 different things, and so that's going to come in 2 versions, a right-handed version and a left-handed version, and so you would want to draw both of those versions. So we don't have to draw both of these products, but we do have to draw this because they're the same, but we do have to draw it twice, once with the bond to the chlorine coming out at us, and once with the bond to the chlorine going away from us. So that gives us the 2 different configurations, R and S, that we could get here. And you would get both of those because these carbocations only have 3 bonds. And remember from the valence shell electron pair repulsion, when you have that you use to find molecular geometries, when you have 3 bonds and 0 lone pairs, they push each other apart to give you a trigonal planar shape. So those carbocations are planar. They're flat, and so the incoming chlorine can attack them from either side, either the top or the bottom. So you'd end up getting both of those enantiomers in this first reaction. Now, just so we can talk about this a little more precisely, you usually number the conjugated pi system from 1 to 4, and if the hydrogen and the chlorine attack on the first 2, that's called the 1,2 product, and if the hydrogen and the chlorine attack on the first and the 4th carbon, it's called the 1,4 product. In this particular case, by coincidence, the 1,2 and the 1,4 product happen to be the same. So that's what happens if this first pi bond attacks the hydrogen. What if the second pi bond attacks the hydrogen? So in that case, this hydrogen will go here. Hydrogen can only form 1 bond, so the electrons that are going to it already will leave. And so after our first step, we would have, now this hydrogen can go to either side. So either the hydrogen, because both of these positions are secondary. So you could imagine the hydrogen either, so let me duplicate this. You could imagine the hydrogen either going here, in which case you would have a positive charge on that other carbon, the one that just lost the electrons, or the hydrogen can add to that carbon and you have a carbocation further away on the other carbon. Now both of these are secondary carbocations. The carbon that has the positive charge is bonded to 2 other carbons. But the carbocation on the left is much, much, much more stable because it's allylic. Because this positive charge is allylic, it's spread out through resonance. These electrons are going to spread out, these parallel p orbitals here. The electrons will spread out over all of those atoms, and anytime you spread out negative or positive charge, it stabilizes it. This positive charge is too far away from the double bond to be involved in resonance, and so it is not as stable, and so that's not the product you'd get. The hydrogen would only add on the right side there. But here we do have that resonance pattern, and so we have to draw those brackets and warn the world. Draw the brackets, neither of these structures is going to be the true structure, only the average of the 2. That's what that resonance arrow is saying, is the true structure. So when you have an allylic positive charge, the curved arrow pattern that goes with that is that those pi electrons go toward the positive charge. So you'd end up with the pi bond here and the positive charge on the end now. So when the chlorine left, when the hydrogen was attacked, the chlorine was kicked off. Now it is living a beautiful and fulfilled life as a nucleophile. We can notice that by that full negative charge, and it could attack either of the positive charges here. It could attack either of those electrophilic positions. So if it attacks this position on the left, then we will get one product And if it attacks the electrophilic position that's clear on the resonance structure on the right, then we would get a different product. And if we were classifying these, we would say, okay, the hydrogen is adding to carbon number 1, or the hydrogen added here to carbon number 1, the chlorine to carbon 2, so that's called the 1,2 product. And here, the hydrogen added to carbon number 1, and the chlorine to carbon number 4, so that's the 1,4 product. So altogether, if you did this reaction, you would get a mess. You would get 4 different products. 2 of them are these enantiomers that we talked about before, and then the other 2 are these 2 products you'd get here. And the mechanism includes everything that we've drawn in. So if we try to do that same reaction with this next one, a similar thing is going to happen. So we will, let's draw in those pi bonds. And then we're going to be reacting that with hydrogen chloride. The pi bonds are nucleophilic centers. Chlorine is electronegative, so it's slightly negative. It steals electron density from the hydrogen, which becomes slightly positive. So we have these 2 different pi bonds, and since the molecule is not symmetrical, these pi bonds are different. So we're going to have to think about this reaction happening twice. Either this first pi bond will attack, that's the one we'll think about first, or the second pi bond will attack the hydrogen. So we'll think about that separately. So if the first one attacks, the nucleophile here attacks the only electrophilic thing, the slightly positive hydrogen. Hydrogen can only form 1 bond, so the electrons in the bond that it's already in get moved onto the chlorine. That chlorine already has 3 lone pairs. It's about to get another one. And when we see that, we end up with the hydrogen actually going where you might not at first expect. So you would have that pi bond there. The hydrogen could either go to the carbon on the left, in which case you would get a carbocation here, or the hydrogen could go at the carbon on the right, in which case you'd get the carbocation here. Now at first blush, you'd look at this and you'd say, well, this is a secondary carbocation. The carbon with the positive charge is only bonded to 2 other carbons. This, on the right, is a tertiary carbocation. That carbon is bonded to 3 other carbons. So you would think that that carbocation would be more stable, but resonance stabilizes charge even better than the carbons donating their electrons. And in this structure on the left, the positive charge is allylic, which means that it's stabilized through resonance, and this other pi bond donates its electrons to help stabilize the positive charge. So because this structure on the left has an allylic positive charge, it is more stable even than a tertiary carbocation. So that's how the hydrogen is going to add there. And because we have an allylic positive charge, we know we have resonance. So we have to warn the world with brackets. Those brackets are telling people neither of the structures we're drawing here are the true structure. The true structure is the average of these 2. To draw the other resonance structure, the curved arrow pattern is that the pi electrons go toward the carbocation. They go toward the positive charge. So we'll have our molecule here. Our double bond will be here now, and the positive charge will be over here. So let me erase that arrow. These are our 2 resonance forms. So that's what happens to the carbon chain. When the carbon chain stole the hydrogen, the chlorine became a nucleophile. It changed its path in life, and it became this strong nucleophile with a full negative charge. And that nucleophile could attack either of the electrophilic centers in the two resonance structures. It could attack the positive charge on the left, that electrophilic center, in which case you would get this top product here. Or it could attack the positive charge in the resonance structure on the right, in which case you would get this next structure down here. And just to keep up with that terminology, if the hydrogen and the chlorine are attached right next to each other, that's the 1,2 product. If they're attached far away, then it's the 1,4 product. So you end up getting those two products if this first pi bond attacks the hydrogen. What happens if the second pi bond attacks the hydrogen? Well, in that case, the hydrogen loses its electrons, and the hydrogen is going to go to the carbon that produces the most stable carbocation. And the most stable carbocation is the allylic carbocation, because that is stabilized through resonance. So even though if the hydrogen went in the other place, it would give you a tertiary carbocation, this carbocation that we've drawn here is the most stable one because it is one atom away from an atom in a double bond, and that means that it's stabilized through resonance. The pi electrons here move over and spread out to help stabilize it. So that's our carbocation, but because it's allylic, we have resonance, so we have to warn the world by drawing those brackets. Those brackets are telling people neither of the structures inside here are the true structure. The true structure is always only the average of the two. So take the average, that's what that arrow is telling you, of these structures. And to draw the other resonance structure, the curved arrow pattern is that the pi electrons go toward the positive charge. So here you'd have the pi bond here now, and the positive charge would be over here. So you have these two structures, and in these two structures, there are two electrophilic centers. So that chlorine that was kicked off with the electrons, that accepted its fate as a good leaving group, and now wandered the world with a full negative charge. After 40 days in the desert, it sees these positive charges and it wants to attack them. So it could attack the carbocation represented in the resonance structure on the left, in which case you would get this first product, or it could attack, and let me just put the hydrogen back in there so you see, or it could attack the positive charge in the resonance structure on the right, in which case you'd get this next product. And so those, if you wanted to classify them, you added the hydrogen and the chlorine next door, that's the 1,2 product. And if you add the hydrogen and the chlorine 1 and 4 away, that's the 1,4 product. So when you do this addition reaction to this conjugated pi system, you end up getting quite a few products. Again, you get a mess here. And so you get all 4 of those products through this mechanism here. And in the question, they were asking you to draw the mechanism for that reaction. So that's what that would be. This next exercise is not quite as hard because the molecule is symmetrical. So you'd see this line of symmetry down here. So we really only have to do, you can see here, we had to draw two different scenarios, one where one pi bond attacked, another where the other attacked, because the molecule wasn't symmetrical, so those pi bonds really were different in different three-dimensional environments. But because we have symmetry in this next molecule, we only have to do that once. These two pi bonds are actually in equivalent spatial environments. So one attacking the hydrogen or the other attacking the hydrogen, it's the same thing. So our first step is to recognize the nucleophiles and the electrophiles. The pi bonds are nucleophiles. Chlorine is electronegative. It pulls electrons to itself, becomes slightly negative. The hydrogen loses those electrons and becomes slightly positive. And so the pi electrons in the conjugated pi system attack the hydrogen. It doesn't matter which one you choose, since the molecule is symmetrical, they'll give you the same product. So after that first step, you have the hydrogen adding at the top, because that gives you the most stable carbocation, which here would be a tertiary carbocation. If the hydrogen added on the other carbon, then you'd only have a secondary carbocation. And not only is this tertiary, but it's also allylic. So you'll notice if you go one atom over from where the positive charge is, you're at an atom in a double bond. And that means that you have resonance. So you draw the brackets that warn people neither of these structures is going to be the true structure. The true structure is always only the average of the two. That special resonance arrow is not telling you that this is turning into that, and that's turning into this. That would be an equilibrium arrow, which is a very different thing. This arrow is telling you the true structure is only ever the average, and neither of these structures ever exists. So, to predict the other resonance structure, the pi electrons go toward the positive charge. And so you'd have this structure right here with the positive charge at the bottom. So when the hydrogen was attacked, the chlorine left. The chlorine has those three lone pairs, and the chlorine took those electrons and left as the leaving group. And so now it's still floating around in the solution as a nucleophile. And that nucleophile could attack either of the slightly positive positions on this molecule. So on the one hand, it could attack the positive carbon here, in which case you would end up getting this product. Or it could attack the positive charge on this other resonance structure, in which case you would get this product. That product there. And if you notice, the places where the chlorine added are chiral centers. They are surrounded by 4 different things on each side. And so each of those actually duplicate into 2 more structures. That chiral center could either be right-handed or left-handed. There's no preference because the carbocation that was attacked is flat. So the chlorine could either attack from the top, in which case it would be coming out at us, or the bottom, in which case it would be going away. Again, it could either attack from the top, in which case it would be coming out at us, or it could attack from the bottom, in which case it would be going away. And so you get a mixture of all 4 of these products if you did this reaction. So I'm going to do these other exercises in a separate video, just so that these videos don't